This is Lecture 5 of the Quantum Formalism Differential Equations Review Lectures. Today we'll be discussing non-homogeneous second-order linear differential equations. Okay, so the first thing we'll do is superposition principle for non-homogeneous equations. And the proof is basically the same as the superposition principle we did for homogeneous equations. So what this one will say is if you have two solutions to the same non-homogeneous differential equation, so we have the same g of t here, then if you subtract them, that will be a solution to what's called the complementary homogeneous differential equation. And that's where you replace the g of t on the right-hand side with a 0. So the left-hand side's the same. Okay, and yeah, this is just because the left-hand side of the differential equation is a linear operator acting on y, so when you subtract two solutions plugged into the left-hand side, when you subtract the two solutions and plug that into the left-hand side, that's the same as taking the left-hand sides with each solution plugged in and subtracting the two of those. And so you'll end up subtracting the two g of t's on the right-hand side and get 0. So here's that calculation written out. Right, the derivatives here and here, y prime, y double prime, will play nice with subtraction. Now you just plug that into the differential equation, plug it into the left-hand side. So that's this first line. And then on the second line, we're just collecting all the terms with y1s and all the terms with y2s. So you'll end up with y1 plugged into the left-hand side of the differential equation. That's a solution to this one, so the left-hand side should be equal to g of t. And then you'll also end up with y2 plugged in the differential equation. That's also a solution to this differential equation, so you'll also get g of t. And of course, g of t minus g of t is equal to 0. All right, so how does this help us solve non-homogeneous differential equations? Well, how it works is if you have a solution capital Y2 to this non-homogeneous differential equation, just one single solution, then that's enough to write down the general solution, because any other solution can be written as some homogeneous solution plus that Y2, right? So we know that if we have some other solution capital Y1, that when we subtract these two, we should get some complementary homogeneous solution. So maybe I'll write that as like yc or something. So that means y1 is equal to this yc plus y2. So y2 is some fixed solution to the non-homogeneous equation, and yc is some solution to the homogeneous differential equation. But if we allow this yc to vary over all the homogeneous solutions, then we'll pick up all the non-homogeneous solutions with this expression, because any difference of two non-homogeneous solutions will have to be a homogeneous solution. That's more or less what's written here. Right, this is saying this will be the general solution, something like this. Y is equal to c1 y1 plus c2 y2 plus capital Y, where yc is what's usually called the complementary solution. This is the solution to that complementary homogeneous equation. And capital Y is just a single solution to the non-homogeneous equation. So that's usually called a particular solution. So we have this decomposition of the general non-homogeneous solution is the general complementary solution plus a single particular solution to the non-homogeneous differential equation. All right, so at least in the constant coefficient case, we know how to find yc, this complementary homogeneous solution. So all that we need to do is figure out how to find one particular solution, capital Y, and we'll have two methods for that we'll discuss today. First is the method of undetermined coefficients, and second is the method of variation of parameters. So I'll start with this one, undetermined coefficients, and this is basically just guessing. So the strategy is we just need one solution, So if we can guess one solution correctly, then we're good. We don't need to know all of the solutions. Just guessing one is fine. And then we can write down the general solution using this formula. All right. And you guess in a somewhat smart way in that you allow a little bit of freedom. You allow some coefficients that you might not be sure of, some undetermined coefficients, coefficients to be determined later to make your guess work. So that's where the undetermined coefficients part comes from. But yeah, it's basically just guessing, and there's some like general tricks and strategies of what things you should guess, but more or less that's how it works out. All right, let's start with an example. Y double prime plus 2y prime plus y is equal to 2e to the minus 3t. And so the idea, we just want to guess one solution to this, and some constant times e to the minus 3t will probably work, right? If you guess a constant times e to the minus 3t, then all three of these terms will also be some constant times e to the minus 3t. Right, taking a derivative of a constant times e to the minus 3t is also a constant times e to the minus 3t. And so as long as you have constants on the left-hand side of this, constant coefficients on the left-hand side here, all those terms will be constants times e to the minus 3t. And so if you pick your original constant correctly, you should be able to make the whole thing equal to 2. That's the idea. All right, so yeah. So we'll guess capital A e to the minus 3t, then capital Y prime is minus 3a e to the minus 3t, and capital Y double prime will be 9a e to the minus 3t. Plugging everything in, we have 9a from the second derivative minus 6a from 2 times the first derivative plus a just from the function itself. And putting that all together, we'll have 4a e to the minus 3t is supposed to be equal to 2 e to the minus 3t. So we just need a equal to a half. All right, so capital Y equals to 1/2 e to the minus 3t is a particular solution. So that is one solution that we were able to guess. And that's all we need, right? Because we can get the general solution just by writing down the complementary homogeneous solution and adding that onto it. All right, yeah, so this one was really not too bad. We just had to take a couple derivatives, plug stuff into the differential equation, and do some really simple algebra. So we'll get to some examples where the computations are slightly harder, but it's never worse than just plugging stuff in and then doing some linear algebra. So not so bad. All right, let's try another example. So left-hand side is the same, but now we have a 5 cosine of 2t on the right-hand side. And so if you want to do something similar to the previous example, you might just guess some constant capital A times cosine of 2t. But as we'll see, that doesn't quite work out, right? Because when you do the first derivative of that, you get minus 2a times sine of 2t. So unlike this exponential function e to the minus 3t, where when you do a derivative, it stays as a constant times e to the minus 3t, this time we'll alternate between cosine and sine. And since there's no sine term showing up on the right-hand side, there's no way this is going to work out, right? We're trying to get like 5 cosine of 2t plus 0 sine of 2t on the right-hand side. So you could choose A to get a 5 cosine of 2t showing up, but then you'd have this extra sine of 2t term there. All right. So that's not going to work, but there's an easy fix. We just have to include a sine of 2t term in our guess. So instead, we'll guess capital Y equals A cosine of 2t times B sine of 2t. So now we have 2 of these undetermined coefficients. So the algebra will be slightly harder in the end. But this time, since both the constant and sine terms are both just going to alternate between cosine of 2t and sine of 2t when we take their derivatives, we'll end up getting just those things accounted for. And then we'll have 2 equations to solve, right? We need to get the cosine terms to have a coefficient of 5 and the sine terms to have a coefficient of 0. But since we have 2 of these undetermined coefficients, 2 unknowns, we should be able to solve both of those equations at the same time. All right, yeah, so first derivative is minus 2a sine of 2t plus 2b cosine of 2t. Second derivative, we'll get minus 4a cosine of 2t minus 4b sine of 2t. And now plug that all into the differential equation and collect the sine and cosine terms. So we have a minus 4a coming from the second derivative times cosine of 2t. Then we'll get a positive 4b coming from 2 times the first derivative. It's another cosine term. And then we'll have an a cosine of 2t coming from the function itself. Then for the sine of 2t terms, we'll have a minus 4b coming from the second derivative. We'll have a minus 4a coming from 2 times the first derivative. And then a b sine of 2t coming from the function itself. All right. And so that gives us a system of two linear equations. So we need the cosine coefficient to be 5, so minus 3a plus 4b should be 5, and then we need the sine coefficient to be 0. So minus 4a minus 3b should be equal to 0. All right, so we'll just need to do some linear algebra to solve those. So multiply this one by 3, multiply this one by 4, and then add those two equations together. The b terms will cancel out, and then we'll be left with minus 9a minus 16a, which is minus 25 times a, and then 5 times 3, which is 15 on the right-hand side. All right, so that'll tell us that a is minus 3/5. Now we just plug that back into the second equation. So we plug the a is minus 3/5 in here. That'll turn into a 12/5. So we'll have 12/5 minus 3b is equal to 0. Or in other words, b is 4/5. All right, so we've solved for these two coefficients. And now we just write down our particular solution. So capital A was the coefficient of cosine of 2t, and capital B was the coefficient of sine 2t. So we end up with a particular solution of capital Y is minus 3/5 cosine of 2t plus 4/5 sine of 2t. And again, we would add on the complementary homogeneous solution if we wanted to write out the full general solution rather than just this one particular solution. All right, so same left-hand side again. Now let's try a t squared on the right-hand side. And you might try just guessing a constant times t squared, but you're going to run into a similar issue, right? Now when you take a derivative, you'll get 2a times t, and then the second derivative will be 2a. So you'll have t squared terms, t to the first power terms, and t to the 0 power terms showing up in your differential equation. And there's no way you're going to make that work with just one undetermined coefficient. Yeah, so first derivative is 2at, second derivative is 2a. Plugging that all in, you'll have 2a plus 4at plus at squared equals t. So you can get the t squared terms to match up by taking a equal to 1, but then you'd have this extra 2 plus 4t showing up on the left-hand side. All right, so that's not going to work, but similar fix. We just need to include the t to the first power and t to the 0 power terms in our guess. Then the first and second derivatives will both have the form of a polynomial including terms with exponent less than or equal to 2. And we'll have 3 undetermined coefficients, so we should be able to solve all 3 equations. So we'll get a coefficient of t squared equal to 1, a coefficient of t to the first equal to 0, and a coefficient of t to the 0 also equal to 0. So that'll be 3 equations we need to solve for, and we'll have 3 unknowns. All right, yeah, so we'll try a general quadratic. Capital Y is at squared plus bt plus c. Then the first derivative is 2at plus b. The second derivative is 2a, plugging everything in. Yeah, so second derivative here, 2 times the first derivative here, and then the function itself here. And now we'll collect the various powers of t, right? So we need 1 t times t squared plus 0 times t to the first plus 0 times t to the 0. So the t to the 0 terms will have a 2a from the second derivative, a 2b from 2 times the first derivative, and a c from the function itself. And that'll need to be equal to 0. 2a plus 2b plus c equals 0. T to the first terms, we have this 4a and this b. That'll also need to be equal to 0. And then there's only one t squared term, and that's just coming from the function itself. So a needs to be equal to 1. All right, so luckily the linear algebra is much friendlier than it might have to, right? Like, we could have run into something with, some kind of system of 3 equations and 3 unknowns with some messy linear algebra, but here we kind of lucked out. We got a equal to 1 immediately, then we can plug that into the second equation right away to get b equal to minus 4. And now plug both of those into the first equation, and we'll get c is minus 2 plus 8. So that's positive 6. All right. So yeah, linear algebra was more or less as friendly as it could be for a system of 3 equations with 3 unknowns. So we'll end up with 1 times t squared minus 4 times t plus 6 as our particular solution for this one. Okay, so the next example, we have same left-hand side, and now 5 cosine of 2t plus t squared on the right-hand side. But these are exactly the left-hand sides of the previous 2 examples, right? This was example 2, this was example 3, which we just did. And so the trick is that we can just add the 2 particular solutions that we got already together to make this new particular solution. And the reason for that is exactly the same kind of superposition calculation we've done already, right? So the left-hand side of this differential equation is a linear operator on y. So when we add the 2 solutions together and plug that in, we just add the right-hand sides. So you can look at the calculation we did back on the first slide, and you'll see, like, if instead of doing y1 minus y2, we did y1 plus y2, then the right-hand sides would add together rather than subtracting out. We also have 2 different right-hand sides this time, but the calculation is still the same. Okay, so we just add up the solutions we already got. So the solution to example 2, which was this one, the particular solution was minus 3/5 cosine of 2t plus 4/5 sine of 2t. And then the particular solution to example 3 was t squared minus 4t plus 6. Add those two together, and we'll get a particular solution to this new differential equation, where the right-hand sides have been added together. All right, yeah, so basically this says you can, like, treat each term on the right-hand side of your differential equation separately if you want to, if it makes things easier. So you can just figure out a correct guess for each term that appears on the right-hand side and then add all of those things together. So that makes things a lot easier. Right? Otherwise, if you were trying to, like, guess all of this at the same time, something for both of these terms, you'd need, like, 5 unknowns and 5 equations. So it'd be like some 5 by 5 linear algebra in principle, which would be kind of annoying. I mean, in practice, all the equations would end up being separate just like we did, but I do think it makes things easier to just sort of decompose the solution in this way and then add your solutions back at the end. All right, so last undetermined coefficients example. Now we have an e to the minus t on the right-hand side. All right, well, so at first glance, you would think, this is just like the first example with the e to the minus 3t term. E to the minus t doesn't turn into a different function when you take a derivative, right? A constant times e to the minus 3t will also just, when you take the derivative, will be a constant times e to the minus 3t. So things should work out all right, but we will actually run into a problem this time, as we'll see. So if we start with e to the minus t, the derivative is minus a e to the minus t. Second derivative is a e to the minus t again. If you plug everything in, we'll have a minus 2a from 2 times the first derivative, and then an a again from the function itself. And these terms will all cancel out to get 0. So here we're trying to get 0 to be equal to 1, and that's not going to work. All right, so equation has no solution. What can we do to fix it? Well, when we were doing the repeated root case for the homogeneous solutions, what ended up happening is when we only had one of these exponential functions as the solution, multiplying by t led to another solution. So like t times e to the minus t might be something that works. And that's not a bad idea. That is the right instinct for sure. So if we try capital AT e to the minus t, let's see what we get. So now we'll need to do the product rule for this derivative. So if we leave the t alone and take the derivative of e to the minus t, we'll end up with this minus t term. And then taking the derivative of t, we'll just get 1 times e to the minus t for the other term in the product rule. Now for the second derivative, if we leave the stuff in parentheses alone and take the derivative of e to the minus t, we'll pick up a minus sign. So it'll be positive t minus 1 e to the minus t in that case. And taking the derivative of the stuff in parentheses, that's just minus 1 times e to the minus t. So we have t minus 1 times e to the minus t, or in other words, t minus 2 times e to the minus t. All right, plugging everything in and collecting the t e to the minus t and constant times e to the minus t terms. So for the t e to the minus t terms, we'll get 1 times a from the second derivative. We'll get minus 2 times a from the first derivative, and then at e to the minus t from the function itself. So those are the t e to the minus t terms. And then for constants times e to the minus t, we'll have minus 2a coming from the second derivative, and positive 2a from 2 times the first derivative. And once again, both of these are 0. So it still doesn't work. We still have 0, e to the minus t is equal to 0. Well, what's going wrong? If you think about it, plugging these functions into the left-hand side and getting 0 means that they're solutions to the complementary homogeneous equation. So these are homogeneous solutions. It's never going to work. So that's the problem. So this will always be the case. If you accidentally guess something that was a solution to the complementary homogeneous equation, you're never going to get some non-zero right-hand side. You're always just going to get 0. Okay. Yeah, so if you look at the characteristic equation, you can see that as well, right? The characteristic equation, r squared plus 2r plus 1, that factors as r plus 1 quantity squared. So r equals 1 is a double root. And so we know that means the general homogeneous solution is c1 e to the minus t plus c2 t e to the minus t. So guessing terms like this and this, that's going to be hopeless. You'll get 0 every time. And the way to fix this is we just didn't go far enough. We just have to multiply by t one more time, and then we're good. So if we take at squared e to the minus t as our guess, then this will actually work. Yeah, so that's the general way to solve this problem. If you are guessing things that appear as part of the complementary homogeneous solution, you just have to multiply by t enough times until those terms are no longer part of the general homogeneous solution. Okay, so guessing at squared e to the minus t, we'll need to do some product rule again to get the derivatives. So leaving the t squared alone, taking the derivative e to the minus t, we'll pick up this minus t squared term. Then taking the derivative of t squared, we get 2t, and leaving the e to the minus t alone, we'll have that. All right, now taking the derivative of e to the minus t, leaving the stuff in parentheses alone, we'll have t squared minus 2t, picking up a minus sign. And then taking the derivative of the things in parentheses and leaving the e to the minus t alone, we'll get minus 2t plus 2 e to the minus t. All right, so we end up with a times the quantity t squared minus 4t plus 2 e to the minus t. All right, and then finally collecting the t squared e to the minus t terms, the t e to the minus t terms, and the constant times e to the minus t terms. What will we get when we plug it into the differential equation? We've got an at squared coming from the second derivative, minus 2at squared coming from 2 times the first derivative, and at squared coming from the function itself. Then we've got minus 4a t e to the minus t coming from the second derivative, and positive 4a t e to the minus t coming from 2 times the second derivative. And once again, both of these terms are going to cancel out. And we're just left with 2a e to the minus t, that term coming from the second derivative. All right, yeah, so what's happening here is if you're writing down like t squared e to the minus t as t times the quantity t e to the minus t, all the terms from the product rule where you're treating this t as a constant are going to go to 0 because this thing solves the homogeneous equation. So you're only going to be left with the terms where you actually take derivatives of both of the powers of t. So that's this 2a e to the minus t term coming from the second derivative. That'll be the only one that's left. All right, anyway, so very simple algebra. We just need to solve 2a is equal to 1. So a is just a half. All right, so we've finally gotten our particular solution. It'll be 1/2 t squared e to the minus t. And the general solution, right, it'll be the complementary homogeneous solution, c1 e to the minus t plus c2t e to the minus t, plus this particular solution, 1/2 t squared e to the minus t. All right, so the last thing that we'll talk about for undetermined coefficients is this table of guesses. So this is what you'll want to guess in general. So this is more or less just going through all the things we ran into in our examples. So if you have an nth degree polynomial, p sub n, you need to guess a general nth degree polynomial on the right-hand side. So you need all of these undetermined coefficients going from tn to t to the 0. You need all of those terms. If you have e to the alpha t, then just guessing some constant times e to the alpha t is good enough. I guess there's a few cases we didn't quite run into, but if you have a polynomial times e to the alpha t, then you want to guess a general polynomial times e to the alpha t. And then finally, if you have a polynomial times e to the alpha t times cosine of beta t, or a polynomial times e to the alpha t times sine of beta t, you need to guess both a general polynomial e to the alpha t cosine of beta t, as well as another general polynomial of that degree times e to the alpha t times sine beta t. And then the last thing is this t to the s that's showing up in all of these guesses, and that's what we ran into in this example 5. That s needs to be the minimal non-negative integer so that no term in your capital Y guess is actually already a solution to the complementary homogeneous equation, because then you're going to get 0 and not whatever you're trying to get on the right-hand side. Okay, so undetermined coefficients, it doesn't work on every g of t. Your g of t has to be of the form of this stuff on the left-hand side of the table. Or you can do sums of these terms as well. That was what we saw in the example 4, right? If you have sums of various things on the right-hand side, you can treat each term separately and then add all your particular solutions on at the end. So polynomials, exponential functions, and then sine or cosine, and you can multiply those things and you can add those things up, but those are the only things this undetermined coefficients method will work on. You also need your left-hand side of the equation to have constant coefficients. That's pretty important, right? So all this stuff that we've been saying, right, like in the very first example where we had a constant times e to the minus 3t, we needed every term on the left-hand side to be a constant times e to the minus 3t as well. So if this 2 were some function of t rather than just a constant, then that will not be the case. You're not going to just get a constant times e to the minus 3t from that guess. So your g of t needs to have a special form, and you need to have constant coefficients. All right, so what do you do if you're not in that situation? That's when the second method will come into play, which is what's called variation of parameters. So this will work for any second-order linear differential equation. It does not need to have constant coefficients. And how it works, you do need to know the homogeneous solution to start with. So yc is c1y1 plus c2y2. So even though this would work for non-constant coefficient second-order equations, we don't actually know how to get the homogeneous solution if it doesn't have constant coefficients. It is the case, though, that actually there are some that aren't so bad. For example, there are things where you can do a change of variables to turn something with non-constant coefficients into a differential equations with constant coefficients, and then you would be able to solve it. So that sort of thing this would apply to. There are some other very special cases of non-constant coefficient equations that you can actually solve. But one useful thing is the g of t doesn't matter. So even if you do have constant coefficients, if your g of t is not something that showed up in the table on the previous slide, variation of parameters will be able to solve that. All right, so assume you have the complementary homogeneous solution, and just like in reduction of order, our strategy is to replace these constants c1 and c2 with functions u1 of t, u2 of t. So we are varying the parameters c1, c2. We're replacing them with functions. That's where the name comes from. And so just like in reduction of order, when we do this, we're going to get a lot of cancellation when we plug it into the left-hand side, right? Because all the terms from where we do the product rule, all the terms where we treat u1 and u2 as constants from the product rule, those terms are all going to get canceled out because y1 and y2 are homogeneous solutions. So that's the idea. All right, so we'll start with y is u1 of t times y1 plus u2 of t times y2. And now y prime, we'll use the product rule. u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. Okay, so now before we go any farther, we'll note that because we have these two unknowns, u1 and u2 of t, but only a single equation, only a single differential equation here, it's reasonable to assume that we can impose another condition and still be able to find some particular solution, right? Remember, we're not actually interested in finding every solution to this differential equation. Just finding one particular solution is enough, because then we just have to add on the complementary homogeneous solution. So if we impose some condition and it gets rid of some of the solutions, that's fine as long as we can still find one solution in the end. And the fact that we have two unknowns and only one equation, it might be reasonable to think we can impose another condition. And the condition we're going to impose is we are going to get rid of these two terms in y prime. So we'll make y prime simpler, and that will also make y double prime simpler as well, right? If we get rid of the terms in y prime, then the second derivative will also be missing some terms as well. Yeah, the reason we want to get rid of those two terms and not these two terms is because these are the terms where we're treating u1 and u2 as constants. And remember what I said, all of those terms are the ones that are going to get canceled out because y1 and y2 are homogeneous solutions. All right, so that's our strategy. We'll impose this condition that u1 prime y1 plus u2 prime y2 is equal to 0. Now we have only two terms showing up in our formula for y prime. We'll still need to do the product rule some more for the second derivative. So we'll get u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. And now let's plug all of this into the differential equation. So, yeah, this is just the second derivative. This is the first derivative. And this is the function itself. And now let's collect all the terms with just a u1 and all the terms with just a u2. So the u1 terms, here's one, u1 y1 double prime. Here's another one. That'll be p of t times y1 prime. And then here's another one, q of t times y1. All right, and then something very similar for y2. So we'll get our u2 and y2. So we'll have a y2 double prime here, and a p of t times y2 prime from here, and then a q of t times y2 from here. All right, and then we're left with two extra terms, u1 prime y1 prime and u2 prime y2 prime. And like I said, here's where all the cancellation is going to happen, right? The terms where we didn't take any derivatives of u1, that will just be y1 plugged in to the differential equation, to the left-hand side of the differential equation. And the terms where we didn't take any derivatives of u2, that will just be y2 plugged into the left-hand side of the differential equation. And those are both 0 because y1 and y2 are homogeneous solutions. Okay, so we've ended up with a pretty straightforward equation. It's just u1 prime y1 prime plus u2 prime y2 prime is equal to g of t. All right, so we've got two equations and two unknowns. This was the condition we imposed, right? That was the condition we imposed to make y prime simpler. u1 prime y1 plus u2 prime y2 is equal to 0. And the second one is what the differential equation ended up simplifying to. u1 prime y1 prime plus u2 prime y2 prime is equal to g of t. And all right, we've ended up, this is just a system of linear algebra equations for u1 prime and u2 prime. So things are working out very nicely indeed for us. So no more differential equations. We'll have to do some integrals at the end to go from u1 prime back to u1, but to solve for u1 prime and u2 prime, we just have to do linear algebra. Okay, so we can write this in matrix form. So we have the matrix y1, y2, y1 prime, y2 prime times the column vector u1 prime, u2 prime is equal to 0 times g of t. And so if we want to solve for u1 prime, u2 prime, we'll multiply by the inverse matrix. That will involve dividing by the determinant. But if you notice, the determinant of this matrix is actually something we've seen before. This is the Wronskian of y1 and y2. And so we know that's never 0. So in particular, like, it makes sense to take an inverse matrix. The matrix will be invertible because we know its determinant is non-zero. At least in the case where like p of t and g of t are continuous, and it makes sense to talk about a general homogeneous solution and such. All right, great. So we can do this. Let's multiply by the inverse matrix. So that's dividing by the determinant. So we're dividing by the Wronskian. Then we switch the diagonal entries and throw minus signs on the off-diagonal entries. So we'll get y2 prime minus y2 minus y1 prime, y1. And that's times the column vector 0 g of t. And because of the 0 here, this will just be fairly straightforward equations for u1 prime and u2 prime. So u1 prime will just be the top right entry times g of t divided by the Wronskian, so minus y2 times g of t. And u2 prime will be the bottom right entry times g of t divided by the Wronskian. So that's y1 times g of t. All right, there we go. We have those two equations for u1 prime and u2 prime. Remember, we're looking for the solution y, which was u1 times y1 plus u2 times y2. So we'll have to take integrals and then multiply by y1 and y2 respectively. All right, so at least in terms of integrals, there are u1 and u2. Just integrate those equations. And now we multiply u1 by y1, multiply u2 by y2, and add them together. So we'll end up with c1y1 plus c2y2 minus y1 times this integral plus y2 times this integral. All right. And so even though we were only looking for one particular solution, like we imposed that condition on u1 prime and u2 prime and everything, we still actually ended up with the full general solution, right? Because this is exactly the complementary homogeneous solution. And so since this is appearing in our equation, we actually have the full general solution. So this thing would be some particular solution if you choose some explicit antiderivatives for these two integrals, some explicit choice of antiderivatives there, then we have this homogeneous, complementary homogeneous solution showing up, and so that gives us the full general solution. So even though we weren't trying to get it, we did actually end up with that full general solution. All right, so that was convenient. Yeah, I will mention, so this isn't the only condition we could have imposed. There are some other choices that would work. One that's actually somewhat useful is you could take just u1, just force u1 to be equal to 0. And then what you would be doing is doing reduction of order at the same time as you're finding a particular solution. So you'd just be working with the homogeneous solution y2, and you would produce another homogeneous solution, essentially using reduction of order, at the same time as cooking up a particular solution. So the calculations will be more difficult, to compensate for that. So that's another choice of condition you can impose. Similarly, you could impose u2 is equal to 0, and then you'd just be working with starting with the homogeneous solution y1 and using this combination reduction of order plus variation of parameters kind of thing to produce a second homogeneous solution and a particular solution. You could make some other choices of conditions to impose on u1 and u2, but pretty much that's just going to lead to like a system of first order differential equations rather than the choice that we made. We got a system of linear algebra equations, which was quite nice. But if you made some other choice of condition to impose, you'd probably end up with like a system of two first order differential equations. And if you had constant coefficients, say, it is quite possible to solve those, but those are usually harder than just solving a given second order differential equation to begin with. So not going to be super useful. So yeah, we made a somewhat arbitrary choice, but it's more or less the only choice we could make to just end up doing linear algebra rather than something to do with differential equations to get these u1 prime and u2 prime. All right, last thing we'll do is an example. Y double prime plus y is equal to secant t. The secant t was not in our table of undetermined coefficients guesses, so we will need to use variation of parameters here. And all right, let's do it. So first we'll solve the complementary homogeneous equation. That one's not so bad. Characteristic equation is r squared plus 1. So the roots will just be plus or minus the square root of minus 1, or in other words, plus or minus I. And so by what we did in the previous lecture, that tells you that the complementary homogeneous solution is just c1 cosine t plus c2 sine t, right? There's no exponential part of these solutions because the roots are purely imaginary. And it's just a 1 inside the 1 times t inside the cosine and sine because the roots are just plus or minus I. All right, so now we can plug everything in to our system of equations from variation of parameters. You could also, jump straight to these formulas, or even straight to this formula if you wanted to, but if you're trying to memorize something, I personally find this much easier to memorize. If you're just looking up formulas anyway, it doesn't really matter, or you could just solve it with a computer, it's all good, but if you needed to do it by hand for some reason, without any references, I find this thing more easy to remember. All right, so let's plug everything in. Y1 is just cosine t y2 is just sine t, y1 prime is negative sine t, y2 prime is positive cosine, and then g of t is secant. All right, so there we go. That's the system of linear algebra equations we're trying to solve. So if we want to do that, we can multiply this one by sine t, multiply this one by cosine t, and then add those together. Then these terms will cancel. We'll get a u2 prime times sine squared t from the first equation, and then a cosine squared t from the second equation, and then cosine t times secant t, but that is just 1. I mean, both of these are 1. Sine squared t plus cosine squared t is 1. Cosine t times secant is also 1, because secant is 1 over cosine. All right, so u2 prime is 1, so u2 is just t plus a constant, not too hard. All right, and now we can plug in u2 prime is equal to 1 right here. Just plug a 1 in there, and then we'll get u1 prime cosine t plus sine t is equal to 0. And so that will tell us u1 prime is negative tangent of t. And you could look up that integral or remember it. If you didn't want to, if you actually want to solve that integral, it's easier to just leave it as negative sine t divided by cosine t dt. And then this is some kind of substitution. V is cosine t, dv is minus sine t dt. Well, that's exactly what's appearing in the equation, right? This is just 1 over v dv in that case. So it's natural log absolute value of v, where v is cosine. So natural log absolute value of cosine t plus c1 will be that integral. All right, and now we just do u1 times y1 and u2 times y2. So u2 was t plus a constant, and y1 was cosine t. I should put it over here. y1 was cosine t, and y2 was sine t. All right, so we'll do t plus c2 times sine t, and this natural log of cosine t plus c1 times cosine t. All right, that'll give us this formula, c1 cosine t plus c2 sine t plus cosine t, natural log absolute value of cosine t plus t sine t. And so this would be complementary homogeneous solution, and this would be some kind of particular solution if you want. All right, yeah, there's no way you would be able to guess this, right? This is not just guessing like a constant times secant t or like two trig functions. There's some kind of like natural log of cosine here. There's no way, right? So guessing is not a good strategy for this one. So variation of parameters is definitely the way to go. All right, yeah, so a comparison of these two methods. Undetermined coefficients, like we said, only works in the constant coefficient case and only works for certain functions d of t, or g of t needs to have a special form. The big advantage is that the computations will only involve linear algebra, and it's linear algebra with constant coefficients as well. So computations are pretty nice, but yeah, only works in certain cases. So usually, if you're able to use undetermined coefficients, it's the way to go, and that otherwise you have to resort to variation of parameters. So you don't need constant coefficients. It will work for any g of t. But your computations, they involve linear algebra, where the coefficients, like the entries in your matrix, are functions of t, and also you have to do integrals. But it's a more general method. Your solution, you might end up with something with integrals that you can't solve, but that's not so bad. All right, so we'll stop there. Here are the quantum formalism links. The next lecture will be the final lecture, and this will be on power series methods.